Our project is energy localization in granular crystals for energy harvesting. Here's a short video on the setup of this project. First, there are n granular crystals in a line. We call each of the granular crystals a bead. So there are in total n beads in this chain. We put rods around the granular crystals in order to restrict their lateral movements. We also apply a static force on both ends to make sure each bead is in touch with the adjacent beads. The granular chain is driven by boundary actuators positioned on both ends of the chain. Both boundary actuators excite the chain over time according to the cosine wave A times cosine 2 pi ft. A is the amplitude and F is the frequency. We analyze two cases of granular chains. One is the monomer and the other is the dimer.
For the monomer case, all the beads are identical in the chain, meaning the mass and elastic coefficient for all the beads are the same. On the other hand, for the dimer case, beads of two different materials are used in the granular chain. The two different materials alternate throughout the chain. In the case which we are studying, the two materials are chrome steel and tungsten carbide. They have different masses and elastic coefficients.
Here is a differential equation of motion for the dimer case. Let's take a closer look. U is the displacement of beads from its equilibrium position. U dot is velocity, and U double dot is acceleration. The bracket plus is defined by bracket x plus equals the max of 0 and x. If x is positive, the output is x. If x is negative or 0, then the output is 0. A is the elastic coefficient of each bead. M is the mass of each bead. Delta is a precompression factor. This system is precompressed by the static force from both ends. Delta measures the overlap between adjacent beads. Tau is a dissipation parameter. Dissipation can be interpreted as the friction between individual beads and rods.
The way we solve these second-order differential equations is to reduce them into two first-order differential equations. If we have a granular chain of 20 beads, each bead has their own second-order differential equation of motion. After reducing second-order differential equations into first-order differential equations, we have 40 first-order differential equations for this system.